The solid inner core and the liquid outer core of the Earth are primarily composed of iron, with some nickel and trace light elements. But at the inner core, where it's solid, the pressures can be up to 360 GPa, with temperatures up to 6,500 Kelvin or so. And the strength of iron at these conditions is important because is important for things like geophysical modeling of planetary impact and planet forming phenomenon. And so the strength can influence how that occurs. And so that, accurately measuring it, in an experiment instead of in models is going to shed light on, these planet forming phenomenon and the structure actually at the inner core. Not only is the Earth, the core of the Earth, iron based, but all of the inner rocky planets of our solar system are also have iron-rich cores, and then there's also some recently discovered exoplanets that are similarly cored structure. But also, you've also got the formation of metallic craters and meteorites. We know that iron is found in about 6% of the fallen meteorites on Earth. And then there's also larger asteroids like Psyche, which is in the main belt, and it's thought to be a remnant core of an early planet. And so understanding the behavior of these constituent materials at the extreme conditions that they're subject to is really crucial to modeling these impact events. Lastly, I also want to mention that iron is actually one of the most commonly used metals here, on Earth for engineering purposes, because it's the main component in alloys like stainless steels or normal steels, which are used, everywhere. Also high entropy alloys, which are, up and coming. And so if we can nail down the behavior of, pure iron, it's kind of like a big stepping stone to more complicated alloys, which, are going to be based on the properties of iron. Next slide. So the shock behavior of materials is important, obviously, because I'm studying shock. And it can be described by the Rankine-Hugoniot equations. So first, I'm kind of just doing a quick overview of shock here. But if you first consider just like ideally a shock as a moving discontinuity where you've got unshocked material on the right and shocked material on the left. So they have different, density pressure states. The wave, the shock front, travels at the sound speed of the material, which causes the particles at that front to move at some certain particle velocity. That increased velocity also increases the internal energy and the sound speed. Next. So in reality, you actually have this sequence of small jumps. And so what happens is that, you've got the very first jump, velocity jump, and then the subsequent one is actually going to be traveling faster because the previous one increased the sound speed. So essentially you've got this steepening of a bunch of these little wavelets that end up forming, the main shock wave. Next. And so Rankine and Hugoniot, in the 1800s, developed this system of equations that can be used to solve for the pressure and temperature, pressure and volume relationship based on a shock. And so the resultant PV relationship is called the Hugoniot, which is the black curve in that graph, where, little blips or something are generally evidence of phase transitions or something. The Hugoniot is also importantly not the path followed from the passing of a shockwave. It's just a locus of the possible end states. The actual path followed from a shockwave is called the Rayleigh line, and that's the red bisector. Next slide. So at the atomic level, shock compression induces a variety of phenomenon. So I'm going to start with like a reference uncompressed lattice in the top left. And then when you start to have that shock wave come through, you start compressing that lattice. So this is just the elastic state where the atoms just start squeezing together a little bit. And at this point, if you had, if that load disappeared, the material would actually be able to recover and return to the reference state. But obviously that's not going to happen in shock compression. You're going to continue shocking. And so the next thing that generally occurs is you have a change from elastic to plastic deformation, where plastic deformation actually alters the lattice structure. And you can see in that bottom left image how the bottom half of that lattice has, the spacing is one amount, and then the upper half, the spacing is a lot smaller. And so you have the formation of many dislocations, which are also tied to the mechanical behavior of materials. And so, everything's connected: structure, processing, properties, it's all connected in materials. But so for shock, if you compress further in some materials, you have phase changes also. At this point, you've distorted that lattice so much that the atoms actually shift into an entirely different configuration. What I'm showing there are just an example transformation in iron from a BCC lattice to an HCP lattice. And so you can see how that perfect cube ends up getting squished a little bit and elongated. And so on the right is, your ideal flat top shock, where you would assume it looks like that. But in reality, it actually looks like this. So next. Yeah, it's a lot more complicated. You've got your region of elastic deformation, plastic deformation, phase transitions. So you can see how they're all, I kind of color coded them. But it's a lot more complicated, realistically. And then at the end of that profile, you can see the spall strength. And so that's the main topic of this talk. Next slide. So spallation is that dynamic failure process that causes high velocity ejection of material. I really like the set of images on the left. It's actually, I think, a GIF normally, but I kind of snapshotted them and put them in the series. But it's a really small aluminum projectile impacting a plate, and that projectile doesn't necessarily puncture the plate, but instead you end up with this large spall scab flying off that back surface. It's just a really cool cross-sectional image of the event. But the images on the right there are newer, higher definition, and you can see that there's a lot of fragments coming off. The spalled iron nickel that I have is actually one of the recovered samples from my experiments, and you can see how that crater, how that crater just kind of ejects off the back. And in both of these cases on the right there, the velocities were on the order of kilometers per second, and so that's incredible speed that can really damage anything that it impacts. So obviously this is all really interesting, but why does it happen? So next slide. So projectile or laser impact essentially generates a compressive wave that ends up interacting with a free surface, causes reflection, and then causes spallation. So I'm going to break this down a little bit more. The schematic on the left shows the movement of a pressure wave. If you think of like a metal sample on the left side and then a vacuum on the right, that's what a free surface is. It's not a junction of two materials, it's a material and a vacuum. And so as that pressure front, moves through and hits that back surface where, the shock impedance between a metal and a vacuum is so different, you actually get a complete reflection of that wave back into the material. And so eventually you can see how that incoming and that reflected wave start interacting until you get this completely negative or tensile wave And that tensile wave is the cause of spall. If those stresses were large enough, you actually tear the material apart. So that's what I'm showing in the simplified drawing. It's that spall scab flying off the back. And then Visar, which is generally what we use for laser shock experiments, is what we use to measure the velocity of that back surface. A lot of spall experiments also happen with gas guns, because you can get really nice big samples with a lot to analyze, whereas in laser shock you're really limited to really small bits, and it's hard to recover material. So from the Visar, or the velocimetry, next, there we go. Yeah, we get a curve that looks like that. It's a pretty simplified kind of characteristic spall velocity curve, where each point, I'm going to describe each point right here, and then we can tie that to the equations. So at point A, you have the arrival of that shock front at the back surface. It just hits, and then point B, you actually have that wave has peaked. So it's not necessarily a triangular wave like I showed in the time evolution on the left there, but it could be a Gaussian or something. And so point B is the peak of that wave, and then at point C, that entire shock wave has reached that free surface. So you actually end up doubling the velocity between points B and C, and that's actually important in a moment. But essentially at that point, once that entire shock wave has reach that free surface and starts reflecting, you end up decreasing in velocity because you're starting to form that tensile region. And so you're canceling, you're kind of canceling out the velocity and the pressure. And then eventually you start, actually failing and spalling. And then that's why you get these weird reverberations at late times. What happens is, if you look at the drawing, that's showing just a simplified one spall scab flying off. But in reality, you actually have a bunch of these, failing layers forming and opening within the material near that back surface. And so, if you imagine you have a bunch of these internal cracks, you have more and more of these wave reflections and interactions. And so that's why you end up with this weird, reverberating velocity curve. So from this curve, it actually tells us a lot of information. So that peak velocity at point C and the pullback signal, which is point E, are used to calculate the strain rate and the spall strength. And then I have a little another example of this later, but I also wanted to bring up the point that how I said that between point B and point C, you have kind of a doubling because that shock wave has entirely hit that back surface. You can assume that the peak free surface velocity is double the particle velocity. And so from the particle velocity, we use the Rankine-Hugoniot equations that I just showed to calculate the pressure. And so, these velocity curves are incredibly important, and we get all our information from it. And so it's really crucial in the experiments that we have really good Visar data. Sorry, that was really complicated and a long-winded way of saying this is how we get our data. Next slide. So the reason spall occurs is due to the formation of voids in the substructure, which grow and coalesce to cause failure. Generally, in fracture mechanics, failure occurs because material tears itself apart, whether that is from a crack or a void. And so this is really no different, just occurring at higher strain rates. So the formation of voids can occur from, at a variety of length scales. That's what I'm showing in this image. At the atomic level, at the lattice level, you can have just vacancies or, these lattice level imperfections, which are, maybe not so important in these failure mechanisms because larger scale effects are kind of more dominant, but it's still important to mention. The more important imperfections here are the ones at, the nanometer or the micron scale. So we've got twin and grain boundaries. And so these are a lot more dominant in the failure, in failure because a boundary has weaker bonding than, the rest of the matrix, and it has higher interfacial energy. And so it kind of, becomes a more preferential site for void or crack nucleation. And at the largest length scales, obviously, if you have a not so perfect, metal crystal or something, and you have these larger just particles or inclusions or something, or precipitates, those can actually cause cracks to form and start opening up the structure. Next slide. So another important part of iron is that it has multiple phase changes, and it's in pressure, temperature, space, and those phase changes can change the failure mode. So it's really interesting, kind of interdependence. At ambient conditions, you have this BCC structure. You can see that in the little unit cell in the bottom left there. And then at higher temperatures, you have this FCC structure. But what's important for these shock experiments is the high pressure phase, which is the HCP. And so this transition occurs, at pretty low pressure, maybe around 13 GPa or so. It can vary between, static diamond anvil cell experiments and laser shock, but it's around there. And so most of these high pressure experiments that I'm looking at look at this HCP phase. But in SPAL, because you have that region of tension where you kind of release the pressure, the structure actually reverts back to the alpha phase. So you have this cycle, you go alpha, epsilon, alpha during SPAL. And next. And so this is where the change in failure mode can occur. These are not my experiments, but it's a really nice paper that I clearly read a lot. But at these experiments by Resseguier, at low pressures and low strain rates, if they spalled this iron foil and stayed in this alpha phase, they saw really brittle failure. So a lot of cracks. And you can see that in this cross-sectional SEM image in the top. But if they, increased the pressure and the strain rate that they were achieving and cycled from alpha to epsilon to alpha, they saw a much smoother SPAL surface. And you can see how kind of, it even looks a little flat. And I'll show you some of my post-shock characterization, but these surfaces are really, really dimpled because of voids. And so the mechanism of the phase change is also going to be important for part of my experiments. And so I'm going to just briefly touch on that on the next slide here. Next slide. Thanks. So this phase transition is martensitic, which is really important for us. It means that it occurs rapidly through the shifting of atomic planes. This is in contrast to diffusion-based transformation, where the atoms slowly migrate, across an interface or something. Martensitic transformations are, they happen pretty much immediately. This phase transformation was first found by Bancroft during explosive impact experiments, but since then, it's been studied many times, both with static DAC experiments and with laser shock and anything in between. So these on the left here are recent results from Merkel using diamond anvil cells. And they produced this really nice hysteresis curve that I really liked reading about, because it shows, during compression, how the epsilon phase starts nucleating until you get in, 100%. And then as they start releasing pressure, you see how the alpha phase starts nucleating back. And it's not, perfect hysteresis curve. It doesn't occur exactly at the same pressures during compression and release. It actually happens at different conditions. And what's also important for this in these experiments is that during compression, they saw that the grain size or the domain size was reduced during compression, and then during tension, it actually reverted to something similar to the original structure. And I say this is important because in material science, grains are one of the biggest contributors to strength, where smaller grains generally have or mean that the material is stronger. Next. But during laser shock, the time scale is going to be much shorter than a DAC experiment. And so these are results from Hareliak, over a decade ago. But this is where they kind of propose the main mechanism for this martensitic transformation. First, what you have occurring, and this is because I'm not sharing these slides myself, it'll be interesting to describe, but I'm going to do my best. First, you've got the atoms in this 110 plane, which are the green circles. And when you compress it along the shock direction, which in this image, you can see that the arrow is pointing downwards, you end up compressing those green atoms, and then they end up expanding along the perpendicular axis. So you can imagine if you compress, if you squeeze down on like a foam or something, the axis along which you're squeezing compresses, but the opposite axis is going to start expanding. So that's what's happening. And so that kind of compression and expansion forms this kind of hexagon type shape. But then secondly, what happens is those atoms in that green plane actually shift. So they shuffle a little bit. And so that they essentially, find that shuffling brings them to a lower energy state. And so it's more favorable for them. And so that's how you end up with this hexagonal structure. And so these were, I think they were a 2008 paper. And then a couple years later, or no, these were maybe 2006. But anyway, a couple years after these ones, Hareliak also did a in situ diffraction study. Very similar experiments where they looked at what happens to the grain size. And so in this initially single crystalline iron, the grain size was actually reduced down to 2 to 15 nanometers, which is huge. It's a huge reduction. And it's honestly probably what, engineers only dream of, because it would, produce incredibly strong materials. But anyways, next slide. All right, so now I'm gonna start discussing my results, and I might need to move a little bit faster, but I've essentially performed experiments both at the Jupiter Laser Facility and the dynamic compression sector to study iron spall. And you can see my main questions that I've been investigating, where my three main points are the failure mechanisms, the spall strength, and phase transitions. So we had really thin iron foils of varying thickness depending on the laser facility. And so we just had a simple ablator glued onto the front. And then at JLF, we had the 2 omega laser, and then at DCS, I think it was a 3 omega laser. And what was cool at the Jupiter laser facility was that we actually had this novel recovery technique. We had this transparent, soft gel. It was kind of like Jello, honestly, but it was transparent. So we were able to put it behind this foil and simultaneously take a visor measurement. Because obviously, as I was mentioning, that visor is super important for all of our, metrics. And so we actually got a lot of really nice data. And then at the dynamic compression sector, we were able to do the in situ X-ray diffraction, and you can see how that X-ray beam kind of comes in at that angle. But both experiments were designed to probe very similar pressure and strain rate conditions. And so we tried our best to be able to compare, apples to apples. Next slide. So I also supplemented all this with radiation hydrodynamic simulations because they were able to, provide insight where the experiments can't directly measure it, which, i.e. the internal pressure temperature conditions. And so we can see from the simulations that, the peak pressure would occur at the front, and then it kind of about 100 GPa or so. And then near the back, we have about 60 GPa. So that confirms that, my design did surpass that alpha epsilon transition. And then we also are very interested in temperature because we don't want it to melt, because we're looking at material strength. And, a liquid doesn't have strength. So we see how the temperature can go up to, 3000 Kelvin, and, these come with a little caveat. I haven't really perfected those simulations. And so some further tweaking of the parameters still needs to be done, but you can see how, hydro simulations really, really powerful, and they can provide tons of useful information. Next slide. So the SPAL microstructural analysis after the experiments was able to provide information about the failure mechanism. These are the SEM images that I took from recovered samples, and you can see starting in the single crystal samples, that failure surface is really, really dimpled. And that's generally due to, the formation of all of these tiny voids that tear the material apart. In the smaller grain samples, the poly and the nanocrystalline versions, we see different failure behavior. It's kind of flaking or, streaked. And that, gives us more information that these samples failed along grain boundaries. So these were, our initial hypothesis. Next slide. I also wanted to show this one because it was a really nice image. We saw actually like vestiges of brittle fracture at the edge of the SPAL plane. And so here you can really see how that change in failure mode can occur. So at the edge of the SPAL, where the edge is that, bottom left corner of the SEM image, you see these really large facets. And then towards the center, you see dimples. And so this is explained by this brittle to ductile SPAL transition, which occurs at a critical strain rate. And for iron, that critical strain rate was about 10 to the 5 per second, which is actually pretty reasonable for the edge of the spalled region, because the main strain rate that we measured how shocks decay. And so, we think it's a pretty good dictator that we've got this, failure transition occurring. Next slide. So these are more post-shock characterization. I did EBSD imaging of the spalled plane. So this is electron backscatter diffraction. And in the single crystalline, I found these really, really nice twin boundaries, or what we thought were twin boundaries. I'll tell you in a moment that they really are. And so that goes back to, that drawing I showed earlier where I said twin boundaries are probably energetically favorable void nucleation sites because of their, weaker bonding and higher interfacial energy. And so we were really interested in these boundaries. And then in the polycrystalline sample, you can see in the bottom left image, there's a bunch of small, crack opening locations. And when we do the orientation map, you can see that those cracks open right along grain boundaries. And so that, also ties back to grain boundaries and twin boundaries being important. Next slide. So for those twins, we wanted to ensure they were actually twins. And so I did a misorientation analysis using a MATLAB toolbox. And so first, I was able to actually plot the misorientation between the matrix, that dark pink color, and the twin, which is the lighter pink. And the angle is around 60 degrees, which is actually the proper angle for twin formation in BCC iron. And so that was our first, check marks that these are twins. But this toolbox also actually allows you to do a coincident site lattice analysis. And so this is really, really kind of deep into material science. But it's a coincident site lattice just tells you how many atoms are overlapping between, that matrix and that twin. And so this, I know the legend is really small, but it found that these boundaries are CSL3 or sigma 3 boundaries, which are indicator of twinning. And so, double check marks, those are actually twins, which is really cool. Next slide. Okay, so this is some of my newer results from the DCS experiments. The diffraction results show that epsilon to alpha transition, that phase transition that occurs during the release, actually occurs within 1 nanosecond of shock breakout. And so as a reminder, shock breakout is kind of like the start of SPAL. And so when we look at this, these compilation graphs, and these are still a pretty preliminary analysis. I need to go back and really thoroughly look at the diffraction patterns, but we can see that during compression, we have that BCC to HCP change. And then at those really small positive values, 0.03 nanoseconds, 0.44 nanoseconds, or something like that, we see a BCC peak start forming pretty quickly. And so that was really cool result that, that'll be, I'm writing a paper on that now. Next slide. Okay, so the SPAL strength was calculated obviously based on the visor, and you can see that on the left side. And then when we compiled all of the data, so my experiments from the 2 laser facilities, experiments from the literature, simulations from the literature, and simulations from Carlos, who's our collaborator in Argentina, who did the molecular dynamics for this project. All that data is on the graph on the right. And it all kind of agrees, okay. There's obviously some differences, especially in the polycrystalline in the red, but that's a whole other explanation. But in general, we see kind of this reverse Hall-Petch trend where single crystal iron is stronger than nanocrystalline iron because of the presence of grain boundaries, which weaken the material. And I call this reverse Hall-Petch because a normal Hall-Petch relationship means smaller grained is stronger, whereas here it's weaker because it's a failure process. Next slide. We also obviously did molecular dynamics, as I just mentioned, Carlos did. We have here stress profiles and temperature profiles, where we see that the single and the nanocrystalline strength, that trend follows the experiments. And we also notice that in the nanocrystalline simulations, the failure is kind of delocalized, so that those stress profiles are kind of look more like a plateau compared to the single crystal, where you have this massive drop in that blue curve. The temperature was also measured, where the curves correspond to the entire sample and the points correspond to locally around a void. And though that local void temperature is much higher, and I'm going to touch on that in a moment. But first, I want to show you the beautiful MD images from these simulations. Next slide. Okay, so these are those beautiful images. I love MD images. They look so colorful. Here we have the shock direction, which is initially from left to right, and then the reflected would be from right to left. And so we found that, obviously we have that BCC to HCP transition occurring, and then, during the reflected shock, the opposite happens. And during that reflected shock in the single crystal, these twins start forming, and you can see those in that top image there. And we find that the voids are actually nucleating preferentially at twin interactions, because those are going to be a lot more energy. And then in the nanocrystalline, you can pretty clearly see that those cracks are opening right between grains. Next. And so overall, failure is in fact dominated by void growth and coalescence. Next slide. So we saw kind of apparent melting behavior, and this was investigated through analytical modeling of geometrically necessary dislocations. And so this is what I kind of touched when I said that we calculated the temperature from MD, because in these SEM images, in these really large voids, we see that those inner walls have this characteristic, like kind of splattering behavior that, to me says it melted and resolidified. And so we wanted to look at this, investigate this a little bit further. Next. So we were able to create this analytical model based on a void emitting dislocations. And eventually you have so many dislocations that you've got really high density. And that's what this graph shows, is the dislocation density based on, the molecular dynamics and then various portions of this GND model. And so they all kind of saturate at 10 to the 17. So, they all agree with each other, which is great. And this high dislocation density is also associated with a temperature increase, which also agrees between these two different methods of simulations. And there's also been research out there that has found during SPAL that tensile state can actually depress the melting point. And so, these two facts combined kind of led us to the conclusion that, that we really could have, melting around or inside a void because of the increased temperature and depressed melting point. Next slide. Okay, so this is actually a really cool result, at least I think. The graph on the left is exactly what I just showed, but on the right is more EBSD maps, and then the bottom two are actually dislocation density maps that I was able to kind of calculate from that same MATLAB toolbox that I used earlier. And so it's really cool to see that the numbers, that 10 to the 17 for the models and 10 to the 15 to 10 to the 17 for the experiments, that's only an order of magnitude off or so. And overall, that's actually a reasonable difference because, modeling has certain amounts of assumptions, and, this toolbox that I used has its own assumptions. And so that's pretty close, in our world. And it really shows the importance of, dislocations in this kind of modeling. Next slide. And so I'm just going to touch one more thing on these two maps. In the single crystal, you can see that the regions of high dislocation density in the orange color are really, really obviously circular. And so we kind of explain that in our paper as some void in the subsurface that had emitted dislocations in, really it would be in a spherical manner. But when we're looking at a 2D cross-sectional map of it, we actually see circles. And so that was a really cool correlation we found. And then in the polycrystalline sample, the regions of higher density are actually within larger grains, and those would actually be at sub-grain boundaries. And so when we look at the simulations that correspond to that, that's the bottom right image there. That red dashed line would be the larger grain boundaries, along which failure occurs, as I've been describing. But within those grains, which are pointed out by arrows, you see these are actually dislocation lines, and that means that you have plastic deformation occurring. That's what I mentioned at the very beginning of the talk. And so we have evidence of both intergranular failure, so between grains, and intragranular plasticity, so within the grain. So it was a really cool way to be able to tie everything together. Next slide. So my ongoing work is obviously focused on my diffraction data. That one slide I had in this talk was obviously not enough. There's a couple things I'm interested in. First, and most importantly, is that we see single crystal-like diffraction spots in the compressed data. So, the ambient image on the left, and then we have something that we think is mostly compressed based on our, initial analysis, but we see these bright spots, which are, those are a single crystal diffraction pattern. A polycrystalline diffraction pattern would be more like just rings instead of spots. And so we were really confused by this. And so there's a couple of things we've thought of. We might have just really large grains in the compressed sample that have like a preferred orientation. And so we still see these large spots, and then, maybe the rest of the structure breaks up smaller. Or maybe this is just evidence of unshocked material. So there's a couple of things I definitely need to investigate here, but that's going to be one of my main points going forward. Another portion is the orientation relationship between the BCC and the HCP transformation. So both the forward and the reverse versions. And so you have, this one peak that breaks up into the 3 HCP peaks. And so that's something I also want to be able to kind of determine, because there's a lot of papers out there that do look at this orientation relationship. And so, it'd be nice to be able to agree with those. And then lastly, a grain size analysis would be fantastic to do, but unfortunately, the DCS time we got was in the pink beam mode. So that just means it's not monochromatic. And so it's really difficult to do a grain size analysis because it's hard to separate the effects of grain size reduction or a pink beam in diffraction patterns. And so there's a couple, I could look into this modified Warren-Averback method. And that's why it's part of this ongoing work. Next slide. I'm going to have you go to the next slide and acknowledge everyone, and then I'm just going to leave my conclusion up. So obviously this is a hugely collaborative effort. Like I mentioned, Carlos, who does the MD for the spa work. We also have Eduardo, who does a lot of the MD for our Iron RT project. And then, a lot of people from Livermore, we've got collaborators in Oregon too, but hugely big effort with a lot of great people. All right, you can go back a slide, and I'm just going to leave the conclusions up so I can start answering questions before I have to leave.
Thank you so much, Gaia. We can open the floor for questions. Feel free to unmute yourself if you have any questions you'd like to ask.
Hello, Gaia. This is Felipe Gonzalez. This is a really nice work. Thank you very much.